Okay, so what we have here is an oscilloscope. An oscilloscope is like a really fast voltmeter. It lets you, remember that wave I showed you with all the little data points? It lets you take a whole bunch of volt readings and then displays them graphically. So each unit or grid line represents voltage, and then the distance this way represents time. Depending on how it's displaying it to you, it'll either take a snapshot and display it to you, or if we slow it down enough, it'll start running a scrolling view of things. Okay? So right now, it's, for example, I've got it set to 50 millivolts. What that means is each grid represents 50 millivolts. And we're set to DC, so it's going to read DC. The 50 milliseconds says 50 thousandths of a second will pass between each grid line. Okay, the other thing that an oscilloscope does is, particularly when you're reading real fast, somehow or another you've got to tell it when to take the snapshot and show it to you, and show it to you long enough for you to see it. So, and if it's, if you're looking at 4 microseconds or something, a really, really short period of time, you're not going to be able to see it very long in that short time period. So you have to tell it when to start showing you information. The point that we do that, the thing we do that with is what's called the trigger. So we will set a trigger, and we can put it on any grid line we want. We can even put it off screen. And then we'll set the trigger to be a threshold of voltage. Or if I'm feeding it current, it'll be a threshold of current or whatever signal I'm feeding it. So we can say anytime the voltage goes above a certain value, start displaying the data. So for example, I've now got this set at the trigger level, and I have a little Z that sort of faces this way. That says anytime the voltage is going up, and right now, since we have no voltage at all, its ground just happens to be right here. I can move it up or down scale if I wanted to. And anytime the voltage gets above like that, it'll start showing us the data at that point. And then I can set where it shows it. So I could be reading voltage, and anytime it comes above, I could have it be on this grid line, this one, this one, this one, or that one. And note that the window you're seeing is actually in this frame right here. The unit's actually reading all the way out to here and all the way out to there. So I can set the trigger out here. So I can set the trigger to occur here, even though what I want to see is right there. So anytime I drill in time, it's like we've zoomed in this way. Anytime I go smaller in voltage, it's like we zoomed in that way. So at this point, I've got this set up to read, and I don't know if my values are going to be right. They'll be fairly close. With respect to this unit, I've got it set up as a standard commutator style generator. And I'm going to feed some current into the magnet here, the field magnet. So the field magnet's going to be the stator, stationary. So I'll bring these down. And I'm going to aim for about 1/2 amp. Don't really care what the voltage is. I'm looking for about 1/2 amp. Well, that happens to take it up to about 5 volts. Okay, and you say, well, why isn't this wire getting real hot? It's just a straight wire. It's a pretty long piece of wire. So it's a pretty good amount of resistance. So if you're looking at this scope, now the question is, which way are the pulses going to show up? Are they going to go up, or are they going to go down? Well, wouldn't we need to know which pole is north and south? And then use our left-hand rule? Well, the only way we're going to know which pole is left and south is to know which way the coil is wrapped, which is a little hard to see down in there. But if we knew which way the coil was wrapped, we could use the coil rule and sort of go like that and say, okay, that's the north side. Then use the left-hand rule, okay? And if I'm spinning this way, the motion would be up, current would go this way, and then that would make one side negative or one side positive. Right? So we can walk through this and engineer it. Do you think it's going to do anything if I start spinning it? Which way do you think I should go to make it read positive? Clockwise or counterclockwise? It's a digital clock. There's no way of knowing, right? Yeah, no. All right, well, let's pick a direction. We'll go clockwise. Okay, it's going to take a little bit because remember, all right, so it's going by pretty fast. So let me do this and put hold on. Put a hold on. Okay, now my turning isn't very even and consistent, but it looks like what it was doing is reading negative DC, wasn't it? Going counterclockwise. Okay, so let's go, get it back to 0, so let's go the other direction. Okay, now it's reading positive. Okay, and that's a pulse DC. So our 0 line was right about there. It's building up pulse DC. Now how much? Well, what are we on? 50 millivolts per division. So we're going to go, say, 1, 2, 3, 4 times 50, 200 millivolts or 0.2 volts being produced. Not a lot, but it's not much of a generator either, right? And I'm not spinning it very fast. Now, going back out of here, I can slow things down. Let's go to here. And let's see if we can slow things down. So let's go, let's do 5. Now, as I turn, it's going to take a little bit longer to get on the page. There it is. Okay, see how things are going a lot slower? When I lock that in place, the time compression's a lot slower. Let's kick that back up to 2. Take it off there. Now it's a little bit quicker. So let's go to here and change the volt scale. So here I dropped it down to 0.2 volts per division. See how it's much lower? I can guesstimate the same basic value out of it. And in fact, with most of these, there is a way to turn it on where it's giving you actual hard values. The problem is those values are changing constantly, way too fast to see, unless you hit hold, if you happen to catch the thing you're looking for.
Can you adjust your 0 ref on that?
Oh yeah, I can do just all. This was like a $39 build-it-yourself unit, so it's got some features that are sort of useful, some not so much. Okay, commentator style. Let's kick it up to where it's a little bit better reading. I think 50 millivolts does a little bit better. Okay, so we're going to kick the time out just a little bit. That's a little bit better. All right, so let's get a good spin. Well, we had a real good spin, but then it sort of stopped. Now note what happened is I spun so much that it went right off scale. I got it going fast enough that it took it right off scale because our voltage went up, right? So we agreed that's what would happen. All right, so let's do, let's produce AC instead. Well, that's easy enough to do. We'll just change the brushes here a little bit, and it's going to make some wolf drills there. So align our brushes, make sure they lay down pretty flat. Okay. So now let's make AC. In this case, it doesn't really matter which way we're going. It's actually producing quite a bit more. So let's go here and drop it down some. Okay. Now our 0 line's right here. It's not a very good line though because I'm not spinning it very consistently. I kind of looping along like a Harley. Right? You know, I'm not so good at that. However, this part is still the armature, right? I've still got this hooked up, the half amp running through here. And all the current that's gonna come out has to come through here. All right? So let's see if we can change that. Let's switch these around. So we'll read this as the output. We'll make these guys hook up to the magnetic field, and now we'll take the magnetic field and spin it round and round. And I'll see if I can't get this to come around and hook up over here. Yeah, it got a little funny on me. All right, so now a little away from. If I get too far away from the light, it sort of gets weird, but if I get too close, it gets a little weird. So now let's see if it does the same thing. Okay, so it doesn't really matter whether I spin the armature or spin the armature or spin the field in the world of AC. In the world of DC, if I'm using a commutator, I don't have a choice because I've got a commutator, right? But that still produces a reasonably good sine wave. It's a little peakier than I'd like. Part of that's because I'm jerking it. The other part of it is the relationship or shape of the field that's spinning around, the magnetic field that's being made. This isn't very good. So what's happening is I'm getting magnetic lines that aren't very clean coming out. They're actually sort of wrapping around this way as much as they can. So that causes it to sort of resist building up, and then it shoots way up and then comes back down. So it does a whole lot of peaking here, not so much here, right? If I made this a little bit more circular and played around with it some, I'd end up with a little bit flatter, a little bit more of a sine wave like action. So that's still a form of a sine wave. So you guys with me, this thing produces electricity as a commutator style, as, okay? And then you can also see the use of an oscilloscope. Could we see that with a voltmeter?
No.
No, absolutely not. Now, that said, an oscilloscope takes a little bit of time to figure out how to use. In fact, the only way to really get good at it is get one and start hooking it up to a bunch of stuff and seeing what it does.
Would a voltmeter give you an RMS, an average reading?
Sure.
Yeah.
Well, based on how fast I'm spinning it.
Yeah.
But, oh yeah, absolutely. If we hooked a voltmeter up to this and I started spinning it, it would give us something, right? Don't know what it is, but from here, what I know is I'm getting peak to peak. So we're saying on the 1.1 volt scale, 0.1, 0.2, almost to 0.3. So peak to peak is 0.3, right? Half of that is 0.15, and then that times 0.07 gives us the DC equivalent, right? Are you with me on that? All right. Okay.
What's the 0.07?
So basically, that's what I did right there. I just flipped things around, spun the field. The output was about the same. If I wanted that DC or that AC that was coming out of here, now that I flipped it around, I'm gonna have to invent something to do that. Okay, but there is something that we got that we can do that they did invent. Okay. So the other problem is if I design the field like this, it ain't gonna work that well. So the whole permanent magnet thing typically doesn't work that well. What they often do is they, you know, a little higher RPM motor like a motorcycle engine. What they do is they embed a magnet in the flywheel spinning around, and then put a coil there, and all it sees is a north, a north, a north, a north, and a little bit of a dip into the south as the field collapses. Doesn't work that well. Sometimes they'll embed two magnets in it and give you both the north and the south. But generally, permanent magnet isn't used to produce a lot of power because it's so darn uncontrollable. So instead of making the magnet that way, we're going to change the shape of the magnet. So we've said we can call this a magnet, and if I put my left-hand rule here, this side will be north and that side will be south. If I go the other way, that'll happen. So if I take a coil like that, I can have one side be the North Pole and the other side be the South Pole. So I'm going to set it out there, and then I'm going to take the magnet and have it come out here. So we got the magnet there and have it come out there, and I'm going to have a metal iron end on this end and an iron end on this end, right? And then I'm going to take and close it like this. So now I've got a bunch of north fingers and a bunch of south fingers interlaced between each other. As long as they aren't touching, this is north. So now I've got south, north, south, north, south, north, south, north, all the way around. Now that works pretty well. I can have a whole bunch of north-south combinations in a circle all the way around this thing, right? The downside is the magnetic lines of flux are just going to go straight across from there to there, aren't they? Okay. So what I'm going to need to do is I'm going to need to make somewhat of a gap between them. And then I'm going to have to make a circumference of iron very close to these magnetic fingers as they're going around, so that the magnetic lines of flux find it easier to jump up into the iron, come back around and go back down to the other pole rather than jump across the air. Okay? But if I can get them to jump out and jump back, jump out and jump back, then each north-south combination, I can have one set of windings, and each south-north combination, I can have a second set of windings. Okay? And in fact, if I stagger this a little bit, I can throw in a third set of windings. And end up having 3 complete sets of windings that are staggered a little bit. Okay. So this would be a permanent magnet. I take my north-south magnet and put a couple little end caps on it. As long as they're made out of iron, they're part of the magnet, right? And then I start adding some fingers to it like I did. And then if I put my wire loops in here, then each one of those going by, the magnetic fields are going to cut it. So I'm going to convert it. Let's convert it to an electromagnet. That's easy enough to do. Permanent magnet, we'll just put a wire around it, a couple slip rings. Make it into an electromagnet. Okay. Voila. Now this is pretty easy to make compared to this. Right? The spinny part, all that is just a coil, right? With a couple of wires that come out, you know. A little big loop, okay, insulated, a little coil, plastic thing sticks in there. Make 2 of these things. They just probably cast drop forwards a little bit, and then a little bit of lathe work. They're stuck in there. Okay. And then if I can get these guys fairly evenly lined up, notice the gap that exists between here. The magnetic lines of flux are going to jump across there, but that's a pretty good gap. So if I take a piece of metal and have it really close to here, the magnetic lines of flux are going to jump up into the metal and come back down. But if I put a bunch of cuts in that metal, then there'll be a point where they jump back into here, then jump back up into the metal, and then jump back into here, and jump back up into the metal. Then I'm going to take and fill those little cuts with a bunch of wires. Okay? So each one of these little cuts that exist in here, they will cause the magnetic lines of flux to jump up into one of the bars, go across, and then back down into the next finger, right? So as this thing rotates along, the magnetic lines of flux that are going straight across are now going to jump up in, and then they're going to collapse back out. Jump back in, collapse back out. And as they do that, they're going to cut across each of these wires in here at right angles. Okay? Everybody with me on that? Now the other thing I'm going to do, notice how I didn't make the fingers straight across. They're all tapered just a little bit. I'm going to do that so that my sine wave, instead of being as peaky as you were seeing here, it tends to flatten out just a little bit. It's a little bit smooth. The amplitude's still the same. It's just, instead of being flat in here and peaky on top, it's a little bit more curved, so that up here on either end, you have sort of a flatter, smoother area rather than a real sharp point. Because the sharp point is going to create circuit noise that you don't want. The flatter, smoother point is going to be more controllable. So we'll do a few things to try and make this thing not quite be as noisy. And you can see in both of these, they follow that same plan form. So then we're going to take this field, or the field, and spin it around in an armature that's stationary. And as it spins around, what you're going to see is 3 individual wires that go all the way around. And in these individual wires, it's a little hard to see on this one. I think the next one you show it. What you'll see is a wire comes in and it loops like this, and then it goes and loops and goes and loops. There's an inner one, there's a middle one, and then there's an outer one. And each one of these are staggered. So this bundle goes to there like that. Then the middle bundle goes to here. Then the outer bundle goes to here. Then back to the inner bundle. Okay? So we're going to stagger each one of these a little bit with an even division of 3 all the way around, so that you get even consistent number of loops, right? So you're going to be doing divisions of 6 or divisions of 12, whatever, in terms of laying this all out. So at any one point, one of these sets of loops is going to be sort of maximum, and the other is going to be going down, and the third one's going to be going up in terms of the amount of voltage that it's producing. And we're going to have a north-south and then a south-north. Oh, wait a minute. That's going to cause the current to go against itself, isn't it? We're going to have a north-south and then a south-north. Well, let's look at this now. Let's look at this. Where'd my thingy, my doohickey go? Oh, here it is. Okay, maybe I got that wrong. Okay, that's north, that's south. So we're going to have a south or north to south, but then a south to north. But then a north to south. So then it's just going to fight against itself, isn't it? Oh, wait. I have an idea. How about I'm going to take the wire and I'm going to come in like this and I'm going to go this way. Wee, wee, wee. And then this one I'm going to go the opposite direction. And then this one I'm going to go that way. And then that way. So if I just take each loop and wipe, or each set of loops and go the opposite direction, so that here I'm going south-north, there I'm going north-south, but I've got opposite direction facing wires. So now all the different currents become additive. Again, I don't know what Kool-Aid these guys were drinking when they thought it all up. But once you see how they've done it, it's kind of elegant, isn't it? Okay, so now instead of this big bodacious thing, we've got a whole bunch of these all wrapped up into a very small little packet. The other thing we've done is, instead of having one set of wires going pulse, 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 we have 3 sets of wires going pulse, 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 pulse. Not only that, but note that when I go 1/6 of a revolution, I'm going to go south-north, north-south. Ooh, 1/6 of a revolution, I've gone 1 complete cycle. There, I've got to go 1 whole revolution. Now I'm going to get 6 complete cycles per revolution. And I got 3 phases doing 6 complete cycles, all staggered a little bit. So I'm actually going to get 18 complete cycles per revolution. And all of that versus this big huge thing, and it's going to get 18 times less. Or 1/18 of. Ooh, it's going places already. Okay. Okay, so in this particular case, now one of the issues here is we're going to have to schematically draw a picture of a coil here. We're not going to draw each one of those little bitty individual loops. What we're going to do is we're just going to go loopity, 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 and presume you understand that in fact what we're talking about is the one circuit that does all those counter-rotating loops all the way around. Okay? And in truth, well, we don't really care how many there are. It's nice to look at it and figure out that it had to be symmetrical, but schematically we don't really care. So when we look at this, now this diagram does a better job of showing the 3 phases. So you've got V, okay, and then let me start at W, and then this winding is going to be U, that winding is going to be V, and see, these two sort of stagger. The W seems to be inboard all the time. V is sort of in the middle, staggers here, and the U stays outboard all the time. What happens is the wires that are going through here. Now this one's actually wound kind of badly. It's going to go like this, it's going to go like that, and then ultimately it's got to run all the way over here to B. If you tighten this up, you can actually have this come out the other side, and then B will sit right there, and each one shares a common set of slots. Okay. Now the other thing of this is when we're done building this, we're going to have 6 wires coming out. Six wires coming out, right? I can hook them up in a couple of different ways. I can hook them up where I have 3 individual wires and 1 common middle wire coming out. I'm going to call that a Y configuration because it looks like a Y. Or I can bring the pairs together, and this looks sort of like the Greek symbol, the delta symbol. So when I look at this winding here, what do I got? 4 leads tells you, especially when this one's big and 3 of the wires come to it, tells me it's got to be a Y wound. That picture that we just looked at, what do you see there? 3 leads with 2 wires going to each one. Doesn't that have to be delta wound? Okay, that doesn't look anything like that little delta symbol. But schematically, that represents 3 sets of coils with each producing some amount of current flow symmetrically. It doesn't show the reverse looping, and the number of loops bear no representation of the number of potential bands that are in there. Okay. So 3 leads, delta. 4 leads, Y wound. If it's Y wound, we have some advantages. Delta wound will give you some additional current, but if it's Y wound, we can tap between any 2 leads, which is going to give us 2 of the sets of coils, or we can tap between the center point, the neutral in the middle, and 1 coil and get half the voltage. So by using Y wound, we can end up having a unit that puts out 2 different voltages. I don't see that. So if I look at this, I can, let's say I got this thing produces, each one of these produce a volt. Right? Here I'm gonna get a volt, I'm gonna get a volt, and I'm gonna get a volt. Here I'm gonna get a volt between here and here, but between here and there, they're in series, so I'm gonna get 2 volts. And I'm gonna get 2 volts here, and I'm gonna get 2 volts there. So if I want 1 volt, I'll hook up to here. If I want 2 volts, I'll hook up to any one of these. Well, that's kind of advantageous. And in fact, part of the reason you'll see most automobile units are Y wound is because its standard was set when these were coming online and being used. There were many vehicles out there that were 6 volt, had 6 volt batteries. So they could just configure it 6 volt or 12 volt by changing how this lead is used. Either everything hooks up to these and that doesn't hook up to anything. It's mounted to an insulator, but it doesn't hook up to anything. Or we hook up between here, here, and there, and we get 6 volts out. So they just sort of have kept that plan for me. All right, so we can use the coils either way. So if we do the Y wound, and we're producing just AC, we can feed that to everybody. So if I take and run that center lead out to your house, instead of having a black wire and a red wire, which is what you see in the DC world, black represents ground, red represents positive, right? This doesn't have a red wire. So instead, we're going to change the plan for them. We're going to say any one of the 3 leads are going to be black. And then the one in the middle, we're going to call it neutral, and it's going to be white. And we don't really care about polarity because it's AC anyways, right? So the black ones, we're going to say they're hot. We don't care positive, negative, they're hot. The neutral is also got electricity going through it. It's just, it's the way for the current to get back to, or interconnect back to the generator, to the other side of the armature coil. Okay? So you can get electrocuted off the white wire. You have to work pretty hard at it. And the reason you have to work pretty hard at it is because the white wire, both of them are copper wire all the way back to the power plant. But for you to take and become part of that path off the white wire, it's a lot more difficult because they're going to send. How do I best say that? I have to think about. Let me think about how to say that better. But you can get electrocuted if you make a really, really good ground. Somehow make a really, really good ground, and you're hanging on to the white wire. The black wire will zap you very, very quickly because on that side, if you're between it and even planet Earth, the power plant, planet Earth, will conduct back to the power plant. Okay? So that's why in a lot of these connections, you'll also see a green wire. And the green wire we call ground or earth. And it truly, that's what it does. It goes to a big, huge copper spike driven into the ground. And back at the generator, there's a big, even bigger, huge spike driven into the ground, which is very conductive. Okay? And then we do that so that rather than going from the white wire through you or the black wire through you, we're going to design the case where it's easier for it to go find the green path back to the planet than go through you back to the planet. Right? So the safety feature, and that's why you have like extension cords, often will have 3 leads. That third round lead is the green wire. The other 2 wires represent neutral and hot. Where you can get hurt between neutral is if you find yourself on between 2 of the phases, the neutral will become a common path between them. So The other thing that's important to note is I don't need all three of those wires. All I need is a neutral and one of the wires. In fact, if I do that, based on what the current has or voltage has been set up, I'm going to get 110, let's say 110 volts out of there. If I go between, instead of the neutral and a wire, if I go between the two wires here, I'm going to get 220 volts. Okay. Or let's say I've stepped up between here and here, I get 220 volts or 240 volts. Excuse me, 220 volts. Actually, no, 440 volts. And then between these two, I get 480 volts. So big industrial applications like the mill, the lathe, etc., they run off of any of these two. And actually, the truth is, they all run off of all three legs. And their motors in those are wound so that there are three sets of windings, each running off of all three of these legs. And that becomes what's called three-phase. Single phase 110 is going to be this and that. Or single phase 220 is going to be these two. But you say, wait a minute, I'm using two of the phases here. It's still being used in one single phase. Okay? So there actually is no such thing as double phase. And every once in a while you see somebody sort of referring to it. It doesn't really exist. I can use all three phases, single phase double voltage, or single phase half the voltage. And if you look at the sine wave being produced by this and the sine wave being produced by this, they'll both be sine waves of the same period, just the amplitude will be doubled. Here, you'll see three individual sine waves, all staggered overlapped. Okay? That's what the phases are really referring to. I know some of you guys have probably heard of the three-phase, but that's why there is no two-phase. It's just all considered to be single-phase or three-phase. Three-phase is the best to get, kind of hard to get. Big industrial facilities like a college or most of Mira Mesa, they get three phases coming all the way into it. But in your neighborhood where you live, they typically only give you two of the phases and the neutral. That way, most stuff in your house is 110, except for the washer and maybe electric range or something like that. They'll have the the single phase 220. Of the three phases, if we label them A, B, and C, you'll get A and B. The guy next to you is going to get B and C. The guy next to him is going to get A and C. And then so they're going to stagger it all the way across the street or all the way down the road. And if you go directly across the street, they're going to also be staggered a little bit. I actually know somebody that bought the house across the street and down one and ran a wire underneath it as a cheap way underneath. It was a dirt road. Just when nobody was looking, ran a wire from the other house that he owned so he could get all three phases. It's way more efficient. Actually ran a couple of wires so both could operate on three phase. The truth is, in big industrial applications, like a building like this or anything where there's a fair amount of current, the power company wants to bring all three phases to you. It's just way, way more efficient. You just don't use that kind of energy in a house. So for them, it's much easier to disperse the load out. It's much more effective for them to disperse the load out across the neighborhood. So that's why often you'll see, I can get 220 in my house, but it's hard to get the three-phase 220. All right. We also may do that in various applications. So for example, if you look at all the benches out here with all the electric plugs to them, they all have a common neutral, but one row of benches will have phase A, the next row will have a circuit, they each have their individual circuit breaker, but the way the circuit breakers are laid out, this one's on phase A, phase B, phase C, phase A, B, C, and then all of the different rows of benches each operate off of a different phase. So if I tried to hook something up to both sides of benches, I could end up getting 220. I could run a lead from the black wire on one row of benches and a lead from one of the black wires on the other, and I'd end up with 220. Right? Don't do that to yourself. Okay. So in all of these circuits we've talked about now, three-phase, single-phase, etc., our output has been 220 or has been AC. If I want to convert it to DC, I can use a circuit called a bridge rectifier, which is made out of these things called diodes, which are check valves, one-way check valves. Okay, they will convert the AC to DC in really a couple of different ways. In half-wave rectification, what we're really going to do is we're going to say the electrons are moving back and forth like this. They kind of go like this, then they turn around, they come back like this, then they go around and they come back like this. Okay? In half-wave rectification, we're going to say we're not going to let them go this way. Go this way. Go this way. Okay, so there's a period where I got a pulse DC and then a nothing. Now I can fill that in if I had a second and a third phase. I can sort of help fill that in. On the other hand, if I could take the electrons that are going to go this way, in one wire they go this way, and when they start going back this way, they'll go back this way in the armature. But if I give another path to the output sees them still going this way. So I go through one part of the armature to here, then my little tricky circuit through another part of the armature to here, and then through another little tricky circuit, another armature here. So now I'm getting full wave rectification. And what that looks like on a scale, so the regular AC wave is going to look like this, right? In half-wave rectification, I'm going to eliminate that. So I'm not going to see the negative side. So it's just going to go burp, burp, burp with a gap between it. In full-wave rectification, I'm going to give this part a path to go a different direction so it looks like it's going positive, like this. So now that starts getting to be like our pulse DC that we saw earlier, right? Okay. Now if I have three sets of windings doing this and I stagger them a little bit, now we're going to smooth things out quite a bit. So depending on whether or not I have one winding or three windings, in fact, if I had 6 windings, it'd be even better. Well, the truth is, once you get beyond 3 windings, 4 windings doesn't help that much, and it's a whole lot more complicated to build it. So all power generation, even in your cars, we use 3-phase, 3 sets of windings. So I don't know if a nuclear generating station, 3 sets of windings. Hoover Dam, 3 sets of windings. Okay. Okay. So to better understand this, what we're going to do, I'm going to show you some pictures that I drew. We're going to plot the voltage through each set of coils. Okay. They'll be equidistant from each other. Because of that, I'm going to use from 0 to 360 degrees to say 1 full cycle, because that's what happens in here. Okay. However, we know when we looked at this, that actual total full cycle only occurs in 60 degrees. So my degrees across this axis, I could have 60 units rather than 360. It doesn't really matter, right? Okay. In this one, I'm going to get 6 full cycles, or 60 degrees per cycle. And this one, I'm going to get 1 cycle per full revolution.
How does the diode know which part to take?
Oh, I'll get to there.
Oh, okay.
I'll get to there talking how that works. Okay. So if we look at phase, in this case, blue, red, green, and we start plotting each one, and in this case, we said each one is 60 degrees apart because we've got 360 degrees for a full cycle. In that one, since we said a full cycle is 60 degrees, each one would be 20 degrees apart, right? And the same relative spacing between each one is maintained. Now, each one of these are drawn because I took a voltmeter or an oscilloscope and plotted this one put it on the chart, then plotted this one and put it on the chart, and then plotted that one and put it on the chart. Or this one, and that one. So the first thing we need to try to do is eliminate the reverse portion of the AC so that the electrons aren't coming back. They're just pulsing forward but not coming back. So we're going to put a couple of these little check valves in the lines leading, we could do it, leading from each coil. Again, but that only really gives us half-wave rectification. We get a delay and the coming back. Now with 3 phases overlapping, it's not too bad, but still we're losing half of our ability to have output. So we can cut the bottom half off, right? But we can, if we use full wave rectification, when this guy is going the other direction, the electrons, rather than going backwards, we can give them a different path to go through. And you won't see it on the drawing here, but we can double this up to where it's producing twice as much current through each lap. Now, for this to be drawn correctly, what I should have done in half-wave rectification is I should have drawn this one, had the 60 degrees of gap, drawn that one, and then done each one like that, and you'd have huge gaps in it. Whereas with full-wave rectification, the part that's going down here now got translated up to this. Okay? Then, if I take all this out, I haven't shown you the circuit, but if I take all of these check valves and arrange them in a series of bridges, what will happen is there'll only be 2 leads coming out. So that means that the output of each phase, when it gets overlapped by the next one, you won't see anything below it. Okay, with the pulse DC, you saw it. But because these are overlapping, as the first one starts to come down, the next one starts to come up, they'll overlap each other. So anything below that gets shadowed. The voltmeter can't see it. The only way I'd see it is if I looked strictly just at one field output. Then I'd see that AC. So it ends up looking kind of like that. I left the first one there. But you end up seeing, if this is my 0 line, this now looks a lot more like DC, doesn't it? Sort of a pulsing, a rippling DC. But I don't go all the way back down anymore. So this as a rectified generator, or as a commutator generator, all it's going to do is give me pulse DC. I get a little bit of overlap by doubling it up, whereas this guy gives me a much smoother output.
I don't understand why you're not seeing the rest of the waves.
Well, when you see the output, you will, because the voltage of this one is now going to be masked by the voltage of this one. So what comes out of the bridge rectifier is this. It's still pushing current. That loop is still pushing current. And this one is still pushing current as it's coming back down until it gets to here. Then it picks a different path through the bridge and starts producing current here. It's just you won't see it on the voltage scale because the highest, you're going to see the highest thing. So imagine it this way. Let's say I have a 10-volt battery feeding into a circuit. Okay? I'm out of places to write. Okay, I've got a load coming down here like this. And let's draw a battery here and a battery here. This one's 20 volts. This one's 10 volts. If I put my voltmeter here, what am I going to read? 30. If I put my voltmeter right here, aren't I going to read 20 volts? Mm-hmm. Okay, the voltage being produced by this is going to be masked.
Okay.
So now red, green, if I draw a third battery, blue. So anytime 20 is higher than the other two, it's what gets shown.
Okay.
Does that help you?
Yeah, thanks.
See it? Okay. Okay. So again, and I said they're drawn 60 degrees apart. In this particular unit, they're actually 20 degrees apart. We don't know for each generator, but it makes sense to have more cycles per revolution. I'm just getting that many more, each one of the little wires being a piston pump, I'm getting that many more piston pumps per revolution. That's a good thing. It'll also make it less bumpy, right? Single cylinder Onan engine, 12 cylinder Jaguar, smooth. Right? Okay. Smooth ride. So when we build this thing and put it all together, it looks sort of like a commutator style generator. And it's got some iron, it's got a bunch of copper wires, it's kind of heavy. Not nearly as heavy for the amount of output. Okay, the weight per amount of output is quite a bit less. They are self-limiting. Okay, remember we talked a little bit about armature reaction? As I spin this around, the more load I put in here, the current flows in here, it creates its own magnetism and the two start distorting. So this magnetic field does that and it does that this way. And the more it distorts, the more stuff gets out of phase, particularly with the commutator. Okay, there's a point where it's going to start having problems. Well, when you look at it in this configuration, where I've got 20 degrees between, now it doesn't take too much armature reaction before it can't do anymore. So it'll self-limit. Anywhere you read on the internet, it'll say, oh, alternators are all self-limiting. That's true. However, they're going to have done a whole lot to make this as light as possible and with only as much cooling as it possibly needs. So this thing, given enough time with the wrench across the leads, will be able to produce more current than it can reject the heat. It will eventually get hot, and hence you see the blackening versus nice shiny copper, black fried insulation, shiny copper, or shiny insulation, fried insulation, shiny insulation. Okay? They make these things a little bit lighter, less cooling than they actually need to reach the self-limiting values in most cases. So you can't overload an alternator. It won't melt it. It won't melt the wire, but it can fry the insulation. This guy, the commutator type motor, it is not self-limiting. If I put a wrench across it, it'll try to put it out. Okay. This one, what'll happen is, let's say I want 50 amps. That's my max output. I want 50 amps. I'll design that thing to have a self-limiting output of, say, 70 amps. So if I put a wrench across it, it's going to go above 50 amps to 65, 70 amps. And after a while, it's going to get hot. It won't go above 70 amps. It'll just sit there and get hotter and hotter. And eventually, I'll smell it, and it'll get lots of smoky, and it'll be ruined. This one, I'll say it's a 50 amps. Commutator, 50 amps. Put a wrench across it, it goes up to 1,000 amps. Because there's no limit. Right? It suddenly tries to do 1,000 amps. Okay, it goes, literally all the solder immediately melts, copper it disintegrates pretty badly because it doesn't have any way of self-limiting the amount of current. So when we get into control, we're not going to worry too much about current limiting on this one because it does it inherently. This one, in the commutator style, we are going to have to protect it against overcurrent conditions because it doesn't internally do it itself. So, and don't buy into the notion that that you can't ruin an alternator by running them with too much output. When you guys go to run your generators out there, take note when you're done with the run. Put your hand on it carefully. It'll be kind of warm. And it'll be a little bit toasty. All right, so take us back to our field that spins around. We've got a north-south, a north-south, a north-south, a north-south, all the way around. Now, unfortunately, when I drew this, I was short by one combination. I needed to have one more. 1, 2, 3, 4, 5, 6, 7. One less or two more. So I didn't end up with a division of 6. So when I looked at the windings, I ended up sort of a little bit wrong. But if I put a bunch of windings around there, and in this particular case, I could have a winding looping like this, and then like this, and like that. There you could use the designators we saw earlier. What was it, W, V, U, W? We could use those. Now we're going to take this thing, we're going to turn it 90 degrees and look at the loops. So now we've got our loops with the magnetic lines of flux jumping into the metal and jumping out. Now, there's no way for me to draw that. Normally what happens is when this piece when the set of wires is right here, that's when it jumps out and cuts. I couldn't draw that well, so we're out of phase a little bit in the drawing. But presume this is maximum here. Because I'm going south to north, I'm traveling this way, and here I'm going the opposite way, and then eventually I go like this way, and then like that way. Each one of these are going to be additive. Each set of wires is going to be additive to each other. So then if I add several more phases, the other 3 phases, and then put an oscilloscope next to it. So now if we look at this, let's say that's where maximum occurs for the red phase, that's where we are. This also partly gets to. Then as I move along, I'm going to get about halfway, and so this guy's going to be headed down, this guy's going to be coming back up. And it's going to come up, and it's going to overshadow, and then once this gets below here, you'll never see it. Just like you never saw the 10 volts there. So now in this case, the green phase takes over and is doing the highest end of the peak. All right, so okay. So and this is just essentially saying what happens here now is as each one comes by, the magnetic field jumps up into the permeable armature housing, and snaps back in, jumps back up, snaps back in, jumps back up, cutting at right angles, and maximizing that cutting relationship. And note how close the proximity is. Okay, that's pretty close. You barely see light through there. Okay, that's way closer than the gap you've got here. So from the magnet's perspective, it's much easier to jump up and go through and come back down to here than it is to go through that air gap. So, however, as I start to get away, the magnetic lines of flux are going to start dropping back into the air and then coming back into the next one and then dropping back in and coming back to the next one. Okay. So, we're going to make a bridge rectifier, but before we do that, we got to tell you how the little check valve works. So let's talk a little bit about how the check valve works. Then we'll talk about the bridge rectifier, and then we'll call it quits for a little lab. Okay. So along around World War II, somewhere in about there, we had invented vacuum tube technology that could act like a one-way check valve. Electrons could go one way, but they couldn't go the other way. And these worked great for fairly low power applications. 5 amps, 10 amps, and of course they got hot, so the more amperes that ran through them, the hotter they ran, the more current you needed to do a lot of things. And unfortunately, in the DC world, we needed quite a bit more amperage. So the vacuum tube solution was never going to be a very good solution. And even at best, under low amperage, they didn't last very long. They did not do well the vibration. So mounted on an airplane or any engine, etc., they didn't hold up well at all. So that kind of rectification was never a solution until along about post-World War II, we invented the semiconductor check valve called the diode. So what we did is we figured out there are some materials like silica, and I talked about this a little bit when we were talking about photocells, where if we put an occasional atom or molecule in there that has a pseudo extra electron, and we take a field of those in one side, on the other side we take and put a bunch of extra atoms in there that are sort of -1. What I'm really saying is I've got an outer shell that's almost full -1, or an outer shell that only has 1 electron in it, okay? So, and then I embed those in a substrate that sort of conducts, it semi-conducts. Okay, I'm going to have a pad here, and a conductor comes out, and a pad here, and a conductor comes out, like that. So what I'm going to do is this is all made out of silica. Okay, silica, the outer shell is half full. And then occasionally I'm going to put some molecules interspersed, maybe 1 per 1,000, 1 per 100, something like that. Okay. And it doesn't really matter what these molecules are. They're interspersed. One could be boron, one could be germanium. Doesn't really matter. All we know is one of them sort of has extra electrons, and the other could use an extra electron. By themselves, just sitting there, they won't do anything. But the energy of the two of them put together is enough to cause some of those extra electrons to jump to this side. I can put those two together, now some of those electrons they're just going to do it. So what's going to happen is a bunch of these are going to go to here, and I'm going to have a region in here. They always show it evenly balanced. It's actually not. It's a little offset. Where all the electrons are going to jump out of here and go over to there. And this area will be depleted. Okay? They're all going to come over here and sit there. Now, if I start adding electrons into this side, what's going to happen is this is going to start building up a negative charge, static charge, and the depletion zone is going to start closing. Okay, and eventually it's going to get to the point where some of those electrons start jumping. Okay, for most diodes, that takes about half a volt to 0.7 volts for this to start closing. Depletion zone to close to where it'll start conducting. But once it starts conducting, it does it in a sort of cascade manner. Suddenly it just starts going. Okay? If instead I go the other way and I take and start shoving a bunch of electrons into here, these are going to get kind of negative, which means the few electrons that are here are going to start trying to push away. And this depletion zone is going to get bigger and bigger and bigger. And harder and harder, and it's going to resist electron travel more and more and more. Okay? So that's the behavior of a check valve. The exceptions are, first, I already said, it's going to take a little bit to open it. Well, isn't that true of a hydraulic check valve? You got a spring there, right? Don't you have to push a little against the spring? So there's going to be a little bit of pressure drop across the spring to open the check valve, right? So that's okay. We expect that. However, in the reverse flow, when the depletion zone is getting bigger and bigger and bigger, the same is, I guess, true of a check valve. If I start reversing the pressure more and more and more, eventually the little flapper valve in there is going to break and rupture, right? The hose is going to break or something like that. Well, that's true with electricity. If I start making this really, really super negative and that really, really super positive, and pretty soon I got 10 million volts, well, 10 million volts will drive a lightning bolt right through the planet, right? Well, it's sure going to go zipping across here. So there'll be some point where the voltage reaches high enough to where now all of a sudden all of the electrons that you've shoved into here that are trying to go that way they're gonna start cascading and they're gonna do it in a very serious, significant way. A whole bunch of current's gonna flow. Okay? And it's gonna get hot real fast and explode. Blow itself apart. Unless, if I dope it a little bit differently, I can actually dope this in such a way that at some voltage, it'll cascade, but in a much more controlled manner, and current will start flowing in the reverse. It's called reverse bias versus forward bias. Forward bias, it takes about half a volt to 0.7 volts. And if I design it to where there's some threshold voltage where it'll go back the opposite direction, we name that a Zener diode. Okay, sometimes said Zener diode. And we can then use that as a voltage measuring tool. So I could design the diode to where at 7.8 volts, it suddenly reverse conducts. And anytime this guy is conducting, I know I'm above 7 volts. And anytime it's not conducting, I know I'm below. So now I got a way of measuring voltage. In fact, I could take a whole stack of these and have different voltages off each one.
What do you mean doping?
Hmm?
What do you mean by doping?
Doping is the art, and this is the magic. Okay, how big is a molecule?
Very small.
Very small. Okay, so for every 100 molecules, I'm at one boron molecule. Another 100 molecules, another boron molecule. Okay, that's kind of difficult to do, molecule by molecule. So they use a process that they call doping, where as they make the silica substrate, they introduce occasional molecules of this other substrate. The process is called doping. The process is actually very different depending on the type of what they're building. Doping is the generic term for interspersing a small amount of this fairly evenly dispersed, in this case boron or germanium or different materials. Okay, that answer? I can't tell you how they actually do it because it's different for the different types of diodes. You can probably look up and find it. So now, when we were talking about solar cells, if that thing's allowed to see light, it'll actually start producing electron flow because the photon energy packets will start exciting some of the electrons and getting them. So one of the things we're going to do when we make this thing is put it in a little opaque package. We're also going to need to make it big enough to handle a lot of current if it's designed to do a whole lot of current. The other thing, and I'm not going to get too deep into it, but we got to connect a metal pad to either side to let current flow through it. We're going to end up having a junction here as well. But these two junctions end up canceling each other. Okay, we're going to say this is going to be P and this is going to be negative material, positive material, negative material. This is going to make one kind of a junction, this is going to make the opposite junction. So these two will cancel each other. However, I point this out because a lot of times this part of it can handle the current, but collecting back into here, this is where it fails. Tends to fail right in there. Not only is it physically a stress riser, but it's also an area that can tend to get hotter than the rest of the diode. So it's not uncommon to see diodes fail there. So we're going to take this array and we're going to design it with 3 leads coming in from the 3 different ends of the fields, ends of the armature output, and then 2 leads coming out. Okay, in this case I used a delta line, but I show a Y one on the next slide. So as this is producing power, we're going to send current this way, and we're going to draw in current the other way. But I've introduced a new symbol here. Okay, that's the symbol for a diode, and we were really smart and clever. We said, okay, diode's a one-way device, so we'll say an arrow going the direction it goes, and the little wall going opposing the direction it doesn't go. Only when we did all this, we didn't know that electricity actually went the other way. So electricity actually goes, if I make this more negative than here, electricity will go the opposite direction. If I make this positive and that negative, electricity won't go that way. Okay, so the arrow points the opposite direction that the electrons actually travel. So, but what's going to happen is, as I take my magnet and I go whoosh across here, I'll draw, we said electrons come in here. So I'll draw, let's see, which ones do they need to come into? It looks like the middle one. I'll draw electrons into here, through here, down across here, out this way, back to here, and out this leg. So they'll come in this leg, through there, and out that leg. And then when it start going the other direction, it'll be a different combination. So that's when I did a north to south, but when I do a south to north, it'll be a different combination of the diodes, allowing that full rectification. So now the electrons, they went this way. Instead of not being able to go backwards, they're allowed to go and go this way. And then and go this way. Right? I don't know how else to describe that, but they basically get a different path each time. Now, symmetrically, in cycles of 3, they'll reuse each of those 3 paths. But, all right, so let's stop here. And I'll go back at this again and again. I don't want to leave you guys too totally confused.
What I'm confused about if the diodes, like you said, change direction. Like you were just changing direction, right? As a diode. What's the difference?
No, what I did is I went through different. I went through different instead of, and you know what flipped was this. Now at some point, this is going to go high. That's going to go high, but this is now going the opposite direction. So now instead of pushing this way, it's going this way. So instead of going this way, pulling up here and going out there, I'm going to go the other way. So I'm going to pull up here and then push out there. So I'm going to use different sets of diodes. So when the electrons are pushed this way, I'll use one set of combination of diodes. When the electrons are pushed the other direction, I'll use a different combination of diodes. I can also sneak back around this way when this guy is down low. So I can do some load sharing off of either side. And the Y-wound can do the same thing. So it's a little hard to show what each electron is doing at any given point. But
Is that just because it operates that way and we're following the rules of how it operates, or is it because we designed it?
we designed it to operate that way.
Okay,
Yeah.
and we're designing, okay.
Yeah, because why throw away why have every north-south but throw away all the south-norths?
Yeah.
If we make 3 phases and then use a bridge rectifier, we get to take advantage of all of them. Now we can do the same thing with a single phase, full rectification, which I think is one of the projects you guys have to work on. If I just take my coil like this and have it come out, and this is my load, whatever my load is. If I just take and put a diode in here, I'm going to get halfway rectification. It's going to be da-da-da-da-da-da. Wait a little while. Might not be a bad idea to also put another diode in here. That's going to stop weird things from happening. However, not the greatest way to do it. If I wanted full ray of rectification, another way of doing it is, let me just redraw that, is if I come out here, this is a little hard to draw. I'm going to go like that, and then I want to draw like this, come to here, come to a point like that. And then these become my 2 output leads to my load. Now, going one direction, electrons can travel this path like that. Going the other direction, they come this path through here, through the same direction, and back that way. So I've given them 2 independent paths. I think this is probably a little easier to see in this single wave.
But you don't get the as fine a resolution on the out.
No, don't get nearly the resolution. Okay, and you also don't get it sneaking and load sharing on the other sides of the windings because you only have one winding.
Where would
Okay.
where would you find this? Is this
All the time, right there in your computer. What are you plugged into?
power supply? Or,
Single phase, right?
Mhm.
You're plugged into single phase 110. So power is going to come out of there and it's going to go into that little biscuit. The first thing they're going to do is transform it while it's still AC. They're going to drop the voltage down to, read the back of it, 19 volts or whatever it is. Okay. Then they're going to run it through a rectifier, convert it to full wave pulse DC. Then they're going to run it into a tank capacitor to try and take that pulsing and turn it into a DC ripple, and maybe a few more filters. Then they're going to put a bunch of other crap in there to make sure the battery doesn't overcharge and a whole bunch of other stuff in there. Then they're going to feed it into the computer. Okay, so anything that needs DC power that's plugged into the wall is going to use something like that. To the degree that you can buy that, the little 4-wire unit and a whole bunch of different load capacities that's got all 4 of the diodes in there. We'll have 4 individual wires that you can wire in, or it's part of an integrated circuit that's already in your little biscuit. Okay, so your shaver at home, plugged in, it's got a little battery, it's got something like that in it. Okay, anything else you can think of, anything that's got a battery that plugs into the wall has to have something like this. If it's really cheap, it might be the other kind where it's just got the 2 diodes. Well, the truth of the matter is it doesn't have to be that efficient if it's your shaver, right? Yeah. Okay, it's a little bitty thing. It's going to charge for 24 hours before you use it again, or 12 hours if you got a face like mine. But in any event, it sort of depends on the application. But all right, so I ran a little bit long. Sorry about that. So let's take a break. I'll get those open.